Welcome back to Upgrade to General, a series to help you upgrade your amateur radio license to general class. This is episode G3, question set B, about radio wave propagation, and I'm your host, Ron Call, KE7CR. Let's jump in. First question asks, what is a characteristic of skywave signals arriving at your location by both short path and long path propagation? Skywave signals are signals that are transmitted on HF up into the ionosphere and refracted or reflected, technically refracted, back down to the Earth. The distance that a signal can propagate by skywave is limited by how high up the ionosphere is and the distance across the curvature of the Earth. It would take multiple skips where a signal goes up, is refracted by the ionosphere, comes back down, reflected from the Earth, goes back up into the ionosphere, is refracted back down again. Those are skips. It would take multiple skips to get around the Earth. Now, if you have a station that is nearer one direction, but the signal can go the opposite direction around the Earth the long way, that's called the long path. The shortest distance between two stations is called the short path. Now, occasionally, you can get signals traveling both directions and arriving at the receiving station. Now, when that happens, they're going to hear a slight delayed echo because of the difference in time that the signals take to travel to the station. Shorter distance takes less time, even at the speed of light. The answer is a slightly delayed echo might be heard. The next question says, what factors affect the MUF, M-U-F? Now, MUF stands for Maximum Usable Frequency. If we look at what factors affect skywave propagation, they're affected by the time of day, because as the sun rises and more solar radiation hits the upper atmosphere, it ionizes more of it. So the more ionized it is, the better it is at refracting signals. So during the middle of the day is going to be the best time for HF propagation on the higher HF bands. The season of the year also affects that. So the ionosphere will be more ionized in the summer. Also, during the height of the solar output, if it's near solar maximum, you're going to have more energy output from the sun, more solar storms. That's going to output more energy that ionizes the atmosphere, and the opposite would be true during solar minimum. Also, meteors and cosmic rays interact with the atmosphere to ionize areas of it. Those have less of an effect than the solar output. So if we look at the answer choices, it says the path, distance, and location. Now, if you're watching the video, this is a chart from an ionosonde. That's where they propagate a signal basically straight up into the ionosphere, and it will refract straight back down to the receiver. And by using these ionosondes, they can calculate the maximum usable frequencies. Now, you need to understand a maximum usable frequency is always the highest frequency possible between 2 points. So down here at the bottom, you can see it's calculated as the MUF for different distances. 100 kilometers, 200, 400 kilometers, up to 3,000 kilometers, which is about 1,800 miles. And you can see the frequency can increase the greater the distance away from the station. So at 3,000 kilometers, roughly 1,800 miles, the MUF is 17, just a little above 17 megahertz. But the closer the station, say at 100 kilometers, the MUF is only 6 megahertz. So when we're looking at the MUF, it also depends on the path distance and the location of the transmitting station relative to the receiving station. The time of the day and the season also make a difference, and the solar radiation and ionospheric disturbances affect that as well. So the correct answer for this question is D. All of these choices are correct. Next question. Which frequency will have the least attenuation for long-distance skip propagation? So understand that the higher the frequency, the more energy these waves have. So they will penetrate the ionosphere better. The lower the frequency, the greater the wavelength, the less energy they have, and so they tend to be absorbed. The energy in those waves is absorbed or attenuated by the ionosphere. So if you want a frequency that has the least attenuation for long-distance skip propagation, you want to go as high a frequency as possible that will still refract and bend back down to the receiving station. So that would be just below the MUF, just below the maximum usable frequency. Next question, which of the following is a way to determine current propagation on a desired band from your station? And the answer here is to use a network of automated receiving stations on the internet to see where your transmissions are being received. The easiest way to do that is to send your call sign out calling CQ and then look on the reverse beacon network to see what areas have picked up your CQ. This reverse beacon network is very useful for seeing what the current propagation conditions allow. Next question, how does the ionosphere affect radio waves with frequencies below the MUF and above the LUF? That's below the maximum usable frequency and above the lowest usable frequency. So between the LUF and the MUF, those frequencies are refracted back to Earth. If the frequency is below the LUF, it's below the lowest usable frequency, then it gets absorbed by the ionosphere. If it's above the MUF, above the maximum usable frequency, like the VHF and UHF, it will penetrate the ionosphere and go off into space. The next question asks, what usually happens to radio waves with frequencies below the LUF? Well, they are attenuated before reaching the destination. Their energy gets absorbed by the ionosphere. They're not able to reach the receiving station. The next question asks, what does LUF stand for? Well, that's the lowest usable frequency for communications between two specific points. Always remember, you have to specify the two receiving points, or the distance, or the skip distance that you want. The next question asks, what does MUF stand for? MUF. That's the maximum usable frequency for communications between 2 points. The next question asks, what is the approximate maximum distance along the Earth's surface normally covered in one hop using the F2 region? Well, the F2 region is the highest region of the ionosphere, and so it's a pretty good distance. The answer choices offer 180 miles, 1,200 miles, 2,500 miles, or 12,000 miles. Well, since the circumference of the Earth is about 25,000 miles, 12,000 miles would be roughly half the circumference of the Earth, so that can be correct. The correct answer is 2,500 miles. You can get almost across the United States, the continental United States, in a single hop from the F2 region. The next question asks, what's the approximate maximum distance along Earth's surface normally covered in one hop using the E region? The E region is much closer to the surface of the Earth, so it's going to be a smaller distance. The answer is 1,200 miles, or 1,200 miles. The next question asks, what happens to HF propagation when the LUF exceeds the MUF? Well, if the lowest usable frequency is higher than the maximum usable frequency, then skywave propagation is not possible. So the answer is propagation via ordinary skywave communications is not possible over that path. And the last question says, which of the following is typical of the lower HF frequencies during the summer? Well, lower HF frequencies, that would be 160 meters, 80 meters. Those frequencies experience high levels of atmospheric noise, or static, which happens mainly from thunderstorms and lightning strikes going on. So it creates a lot more static on those bands. So it's a lot more desirable, if possible, to use the upper HF bands, 20, 15, 12, 10 meters during the summer. They tend to be quieter with less static and atmospheric noise. So that's the last question for this question set. Thanks for joining me. We'll be back for the next question set in Upgrade to General. For now, 73, this is KE7CR.